Hello mathematicians, we now have a look at finding the volume of solids if we know the cross-section. And it's another slicing method. The known cross-section bit maybe would be better worded as volumes of solids with similar cross-sections, because this obviously only works, as you'll see, if we can establish some sort of a similarity relationship. So if we have a uniform cross-section A and a height h, the volume of a solid we know from junior school is given by A times h. So if A varies as a function of h, then we can write this, that we can imagine taking a little thin slice, so that's this part in here, and the thickness of our slice is dh, and the little element of volume is going to have an area which is a function of h multiplied by the thickness of h. So if we take that sum to infinity as we make delta h tend towards 0, that becomes our integral. So in this method, this is our underlying basis, that the volume is the integral of A as a function of h dh. Now the h will become x or y, depending on which way we take the slices, perhaps. So let's apply this method to this one here. Show that the following formula is correct. The volume of a cone is in fact 1/3 pi r squared h, as you would remember hopefully from junior school. So to do that, we know that if we take a slice of the cone, then that's a little circular, it's a disc, I suppose, in a way. But we know that the area of that disc depends on how far up the cone we go. So it depends on the height we're at present. We know that when we're at maximum height, the volume of that disc will be 0, and when we're at minimum height, when we're down on the base, the volume of the disc will be its maximum. So this diagram here sets up some similar triangles which will let us get a relationship between how far up the cone we are and the volume. But we shouldn't lose sight of what it is that we're trying to do. We're trying to say that the little element of volume is equal to the thickness. Now in this case y is the vertical axis, so I'm going dy, times the area of the face. And the area of the face is going to be pi times x squared. So if we come back to our diagram over here, we can see that we can look at similar triangles. If the cone has a height h and a base radius r, then when we go up a distance y, we're going to say that the radius will be x. And what's the relationship? Well, the relationship is simply based on similar triangles, that the ratio of corresponding sides in similar triangles is equal. So the ratio of h in the big triangle to h minus y in the little triangle, so that's where we have to be careful, equals r in the big triangle and x in the little triangle. So from that we can get an expression for the value of x in terms of y. Now the reason we need it in terms of y is because when we sum all of our little slices of known cross-section to get volume, then we'll be summing vertically, so it's dy. So we're going from 0 to h in the vertical direction, and the slice is pi x squared. But we need, if we're integrating with respect to y, we need x as a function of y. So I've just seen what that is, that x as a function of y, when we square it, is this thing, and then we can then do that integral. So the rest of the process is pretty straightforward. Taking out common factors, doing the integral, plugging it all in, and we get pi r squared h on 3. So we've proved, using pretty advanced maths, what you already knew from junior school. Now for our next question, it says a solid of height 2 meters has a horizontal base The cross section at a height h above the base is a square of side length that. So we need to find the volume of the solid. So we imagine a slice somewhere up there at a height h, and we think about that little element of volume. So that little element of volume is going to have a certain area, which we've got an equation for as a function of the height, and it will have a thickness h. So when we substitute in, then the area of the face, because it's a square, is going to be s of h all squared. It probably could have done with an extra bracket around there to show that it is actually the whole of s of h all squared, times delta h. So when we take it to its limit, the volume is the integral of, and dh, so I might as well use h here. There's not much to be gained by switching the variable to a y at this stage. And we're going from a height of 0 to a height of 2. And what have we got? We've got s of h all squared, which is this thing up here, all squared, which is that. And then away we go. We can just do that integral and get our answer just here. Okay, so for our next question, it takes a little bit of getting our head around the shape of the diagram, and my drawing skills are not going to be of any use at all here. So we've got the base of a solid is a circle, so we can see that circle in the diagram below. Each plane section of this solid is cut out by a plane perpendicular to the y-axis. Can't even read it at the moment, but it's an equilateral triangle with one side in the base of the solid. So this is my equilateral triangle with the base in the solid. And if you can imagine the shape that this forms, it's something like a semicircle, a hemisphere with a pointy ridge running over the top and straight sides, but on a circular base. What we have to then do is to say, well, imagine an element of volume in there. So the black thing that's drawn, it's got a thickness delta x. And when we look at that, then we want to get an expression for the volume of that element just there. So the volume of that will be the area of its face times its thickness. Now its thickness is in the dx direction. So if we come down and think about that face down, we can see that what we have is a similar triangle, an equilateral triangle, and the side length is twice this distance here, and that distance is square root of 4 minus x squared. So the expression for the area of that element there will be given by the sine rule, half AB sine C. So we've got a half AB sine C, which with any luck simplifies to that. So that's our expression for the area, and it's a function of x, which is what we wanted because we were integrating with respect to the x-axis. And also I've just gone here, and despite my tendency to lose 2's, I've decided that I'll do 2 times the integral from 0 to 2. So when I come down to my final expression for the volume then, the volume is 2, that 2 there, times root 3, that root 3, the integral from 0 to 2 of 4 minus x squared, which is then entirely doable. So barring errors, that's what we should come down to as our value. Now our next question is a similar style, where we've got the base again as a circle. Each plane section is a square with one edge in the base of the solid, and we want the volume of the solid. So if you have a look at my drawing there, you may be able to see the square, the thickness is in the direction delta x. So we're going to find the volume of that solid element as the area of the face times its thickness, dx. And in terms of x, the area of the slice is going to be given by the length of a side. You can see from the diagram that will be 2 times 9 minus x squared, and that is actually going to then be all squared because it's a square. So that's our element of volume. Therefore our integral is, and again I'm going to double 0 to 3 rather than going 0 to minus 3 to plus 3, and it's the square of 2 times the square root of 9 minus x squared, which gives us that. Just take the 4 out and get the 8. We've then got this integral, and away we go. So with any luck, 144 cubic units is the volume. Now for our last example, we want the volume of a pyramid whose base is a square of side L and whose height is h. We know from, again, junior school that for a pyramid the area is 1/3 the area of the base times the height. So we're expecting to get 1/3 of L squared times h. So we look at our pyramid, we imagine our slice at distance y up from the base, so that the volume of that slice will be its area times its thickness, and because it's the y direction we're slicing and dicing, if you like, it'll be an integral dy, so we need a as a function of y, and we're going from 0 to h. So what is the height as a function of, what is the area, sorry, as a function of y? Well, we know that the area is going to be a square. So if we look at a similar triangle down here, we can see that for this similar set of similar triangles, then h on the big triangle compared to h minus y in the little triangle at the top is L on 2 in the big triangle compared to x on 2 in the little triangle. And the reason it's L on 2 and x on 2 is obviously this triangle here is a slice, is a triangle formed by dropping the perpendicular down through the middle of our pyramid. So when we rearrange that and simplify, we get this as our expression for x, and then the area of our face is x squared because it's a square. So into that we've got, so here's our L squared, it's a constant so we can take it out, likewise h squared, and our h minus y all squared is the variable. We're going from 0 to h in the y direction. So that then becomes an integral that we can cope with just using our ordinary advanced maths techniques, because the power of y is 1. So when we do that integral and do our substitution, we indeed get what we expected, 1/3 of the area of the base times the height. Okay, so now have a go at set 2.